Welcome, everyone, to our presentation on BigONotation. Today, we'll explore algorithm efficiency and performance and discuss why a deep understanding of Big O is critical in computer science. We'll see how this concept is not just theoretical, but a practical tool that helps in designing efficient algorithms. Let's start by defining BigONotation. At its core, BigONotation is a mathematical tool used to describe the performance or complexity of an algorithm. It focuses primarily on the worst-case scenario as the size of the input grows, making it an essential concept for assessing scalability and efficiency. This means that regardless of hardware or specific implementation details, Big O gives us a standard way to compare algorithms. You'll notice a diagram here that illustrates various growth rates: constant, logarithmic, linear, quadratic, which really helps visualize how Big O captures the scaling behavior of different functions. Digging a little deeper, the essence of BigONotation lies in its ability to abstract away constants and less significant terms. This abstraction lets us focus on the dominant behavior of an algorithm, essentially its upper bound in terms of runtime or space requirements. This approach is particularly useful when considering what happens as the input size tends towards infinity, a process known as asymptotic analysis. By evaluating the worst-case scenario, BigONotation provides a reliable basis for comparing different algorithms, especially when scalability is a key concern. Now, let's review some common classifications in BigONotation. O(1) constant time. Here, the execution time remains unchanged regardless of the input size. O log(n) logarithmic time. Algorithms in this class are very efficient, as their runtime grows slowly even as the input increases. O(n) linear time. The execution time grows in direct proportion to the input size. O(n log(n) linearithmic time. This classification is typical for efficient sorting algorithms. O(n squared) and beyond polynomial time. For these, the runtime can become infeasible as the input size grows very large. As you see in this animation, the behavior of each BigONotation. Understanding Big O is more than just a theoretical exercise, it's a practical framework for determining and comparing algorithm efficiency. With BigONotation, developers can choose the most appropriate algorithm for a specific problem, foresee potential performance bottlenecks, and build a strong foundation for tackling more advanced topics in computational theory and algorithm design. Let's consider some real-world examples. When analyzing searching algorithms, we see that a linear search operates in O(n) time, while a binary search is much more efficient with O log(n) time. In the realm of sorting algorithms, comparing bubble sort O(n squared) to merge sort O(n log(n) clearly shows the impact of algorithm choice on performance. These examples highlight the direct impact on software performance and scalability. To sum up, BigONotation is a fundamental tool for describing the upper limits of algorithm performance. It plays a critical role in understanding both scalability and efficiency, ultimately enabling practitioners to make well-informed decisions about algorithm and system design.